All right, so is everyone ready to begin? My apologies for the wait. Alrighty. Okay, everything seems fine. All right, so before we start, Newton's laws of motion, right? So as it relates to Newton's laws of motion, what do we already understand from it? What do we get from it? What comes to mind? There's some concepts that should be coming to mind, right? What are they? Nobody? What are the concepts that come to mind when we talk about Newton's laws of motion? Different concepts. Right. Gravity, resultant forces, the first law. Alright, so really and truly something around there, I guess. Alright, so we have a few things that comes out, right? New Actually the gravitational force, right, is actually not really regarded as one of the laws of motion technically. Alright, so we usually just say there are three laws of motion, and then we start talking about Newton's gravitational force as if it's like as a fourth one, really. But it's not really grouped within the main three laws of motion, because gravitational force comes from those laws that we're about to discuss. Alright, so here, what we're supposed to be doing, alright, based on the syllabus, right, we're supposed to be able to state the three laws, so Newton's laws. Right? What else are we supposed to be able to do? We're supposed to be able to define some concepts, right? So we're supposed to be able to define the concepts of force. We should know what force is, mass. We should know what inertia is. Let me fix that. Right, so hopefully as I'm writing these things, you guys probably know what these are already. And we need to know what momentum is. Alright, so need to know these terms as well, right? What we're gonna be looking at especially as well, right? We're gonna be looking at the principle of conservation of momentum, right? So conservation of momentum, and we're also going to have a look at the different types of collisions, right? So we're gonna look at collisions and the different types. Go ahead. Was that a notification for like a question? Just gonna look at the types. Alright, so that's what we're gonna be looking at in this first section here. Everybody good with that so far? Hopefully everybody's good with that so far. Just give me one moment. Let me just connect my headphones. Just realize that they're not connected. So I can hear you guys a bit better when you guys speak. Alright. Lovely. Can somebody just say something for me, please? So I can know that it's working properly. Oh, there's somebody in the. Lovely. and your hand was raised as well. All right, so let's look at these things. So let's continue. So Newton's first law. So I'll need you guys to speak to me. All right, we're gonna be looking at that, right? So three laws of motion. It relates to, well, let's start with the first law. What's the first law that we look at? What is Newton's first law? Go ahead. Anyone? Go ahead.
A body will remain at rest until acted upon by an external force.
All right. So we're saying that well, it's the body at rest will remain at rest, or a body in motion will remain in motion unless acted upon by an opposite force or some outside force, right? So we're looking at that. So every object continues at rest, right, or uniform velocity, right, unless acted upon by some external force, all right. So we're just looking at that. And why is that really defined as? What do we call the first law of motion? There's a term that we use for it. What's that term that we look at?
Inertia.
Inertia. So we're saying that every object, right, continues. One moment. All right. Every object continues at rest or in or at rather. I should just put at a continuous or uniform velocity. Velocity unless acted upon by an external force. Alright? And as stated before, this is the law of inertia, right? Or we just could just write inertia here. Alright? Everybody's good with this? Everybody should be good with that, right? So we're looking at that for the first law, right? So we're looking at this entire concept, right? But the concept of inertia specifically that we look at in the law, what would inertia refer to? So we call it the law of inertia, but what is inertia? What's the term inertia? Anyone? Casey and Shanique, Danielle, Prudent, Josh, anyone? What is inertia? No clue. Nah, you're lying. I know that you're lying. Alright, lies. What is inertia? Inertia is the reluctance, right? So the inertia of a body, right, is its reluctance to start moving if at rest, and to stop moving if it is in motion. That's what it is, right? So we're talking about the reluctance of an object to stop once it has begun moving, right? And the reluctance of an object to start moving once it was at rest, right? So we're looking at basically how reluctant is the object, right, in relation to force, right? So how hard it is to move the object, right? If it is going to be at rest, how hard is it to push the object or to move the object or to, you know, get it moving once that rests, right? Or if the object is moving, how hard it is or how reluctant it is to stopping, right? So what we're looking at is, um, I'm trying to find a better word or an easier word, but it's generally the reluctance of an object to start moving if it is at rest. and to stop moving if it's already in motion, right? And we can relate this to being heaviness, right? Some persons relate it to being related to an object being heavy, right? If an object is really heavy, it's extremely hard to just push it for it to start moving, right? And if it's really heavy and it's in motion, it's really hard to stop the object. So we can think of it as the heaviness of the object, right? How hard it is to push the object, how hard it is to stop the object once it starts moving, right? We're looking at something like that, right? And really and truly, inertia, right, is really related to mass, right? So mass is a measurement of an object's inertia. Keep on putting in inertia, all right? So mass is just a measurement of an object's inertia, right? Or it is a measurement of an object's inertia, right? So we're looking at this. If something is massive, meaning it has a lot of mass, massive, right? It will be harder to push, right, than if something were to be, let's say, minuscule or small, right? So it's easier to push, let's say, a football than to push a building, right? That's a very drastic comparison, right? But it's easier to push, let's say, a 10-pound weight than a 1,000-pound weight, right? So we're just looking at that. So the larger the mass, the larger the inertia of the object. This makes sense, right? Does that make sense so far?
Yes, sir.
All right, so that's what it speaks to, right? So we're looking at that. So we're looking at whether or not we have some velocity, right? Specifically as it relates to the Newton's first law, right? So every object um, continues at rest or at uniform velocity unless acted upon, right, by some type of external force, right? So we're looking at that in general, right? And that ties into the object's inertia. So if the object is more massive or has more mass, right, you would require a larger resultant vector or a resultant force, right, in order to stop the object from moving or to start the object moving. We're looking at something like that. But before we get into, well, that is really what the first law is about, right? But we also have another concept that we have to look at under the first law. So we have inertia, but we also have the concept of momentum, right? Can anybody let me know what momentum is? What's momentum? In physics, we can give worded definitions or we can give equations of definition, well, as definitions. So what is momentum?
On to this mic. Sir, the rate of change of motion.
The rate of change of motion. Interesting. The rate of change of motion. I, huh. Okay, so I would not, Is this partially right? Hmm. Alright, so at this level, I think I would just like deny that answer. So not technically, right, the rate of change of motion. What you're saying, the rate of change of motion related to like something like that, the rate of change of motion, so change in displacement over time, something like that, that would be velocity, but not the momentum, right? So this is the velocity, but I'm not sure what you're referring to as it relates to the rate of change of motion, right? But momentum, really and truly, right, is the product of an object's mass and its velocity. That's what it is, right? So it is usually represented by P, right, is equal to mv, and the units, the SI units for momentum is what? Anybody? Anyone? Are you guys using the chat? Oh, you guys are using the chat. Oh my. My apologies. I did not see the chat. All right, I can see it now. All right, so lovely. We mass times velocity, right? Okay, lovely. It's not newtons, right? If mass is measured in kilograms and velocity is measured in what? Meters per second, right? Then what are we gonna have as the unit? It's gonna be kilogram meters per second. So kgm per second. All right. So that is what we're looking at here. Okay. Nicely stated there. Okay, lovely. So not newtons, but that. All right. So looking at that. All right. So that's what we normally use for it. So let's say that a car of 500 kilograms, right, is moving at 10 meters per second, right? So let's say object A is going to be, let me just change this back real quick, right? So let's say object A is 500 kilograms and is moving at, let's say, 10 meters per second, right? And then we have object B, which is 5,000 kilograms, moving at 10 meters per second. Which object has a greater momentum, object A or object B? Let's check in the chat now. Object A or object B, which one has the greater momentum? B. Alright? So this has the greater momentum. Really, really simple. Alright, so as it relates to momentum, PA and P of B. Well, no, let me fix that. Alright, P of B, right? The momentum of B would be actually greater than the momentum of A. Alright? That's fine. So that's literally what the first law really is, alright? That's done there. So let's move on to the second law. So Newton's second law. So second law. What is the second law? I'm gonna write it out here though. So anyone, what's the second law? I would love for you guys to unmute and explain to me what the second law is. What do you know from the second law? What is it? What's Newton's second law? Yeah, but we're gonna get there. We're gonna get there. So in words, what is Newton's second law? So it speaks to the rate of change, right, of momentum. So looking at the rate of change of momentum of a body, right, and it is directly proportional. Let me just move over. Proportional, right, to what is directly proportional to the applied force, right? Proportional to the applied force and occurs in the direction of the force. And it occurs in the direction of the force. My bad. Alright, so what does this speak to? So that's what we have for Newton's first law, right? So It is the rate of change of momentum of a body, right? Or the rate of change of momentum of a body is directly proportional to the applied force and occurs in the direction of said force, right? What does it speak to, right? So let's look at this, right? Suppose, let me just write the word boldly, suppose, right? So suppose we have a force acting on a body F, right? So the force acting on a body. We have that there, right? The mass of the body, right? M of said body. And we also have, right, the velocities, right? U and V. What would U be? I just saw your comment in the case, and that is not the second law, right? But let's look at this. What would U be? The initial velocity, velocity actually, and then V would be final. So we're working with that. Mm-mm-mm. Okay. All right. So we have that there, no problem, right? So suppose we have these variables, right? What we're going to be looking at here is a change of momentum and the change in momentum. Because what does the law state? The rate of change of momentum of a body, right, is directly proportional to the applied force and occurs in the direction of the force. So let's look at the change of momentum or change in momentum. All right. Looking at that, the change in momentum, right? So momentum is equal to what, right? We must recall that momentum P is equal to mv, all right? And from that, right, let me actually just change this, right? Because I'm going to be deriving the second law, and I don't know, it's just a general rule for me. I do all my derivations in purple. So let's just change that. But yeah. So before we start, right, what we're going to basically be doing, right, is deriving that law. So let's look at this. So recall that momentum is that we have to look at change in momentum, right? So change in momentum would be the momentum of the object with the final velocity, right? Minus the momentum of the object with the initial velocity, right? Do we agree? Drop a 1 in the chat if you agree with what is here. Alright, so we agree. So final momentum minus initial momentum. Because we can see the velocities, right? So we have that there. My apologies, right? So we're looking at the change in momentum with respect to time, right? So that is the change of momentum. So what would be the rate of change? The rate of change would simply be the change in momentum, right? Once we have a rate of change of something, we're looking at it with respect to time. So we're looking at the rate of change here, right? And that is simply equal to delta P, which is the change in momentum over T. Following there as well? Shanique, do you see what's going on? Daniel, do you see what's going on?
Yes, sir.
Prudent, do you see what's going on? Alright, so we're seeing what's going on. Alright, so we're looking at that. So now, let's have a look at this. We are saying that this is equal to the force. So the force is equal to the mass, right? So let's just factorize this real quick. Dragging out the mass because the mass is same in both of them. Mass times V minus U, and this would be all over, this would be over T, yes? Makes sense, right? Recall, right? We're recalling now, right? From the first kinematic equation, Recall from the first kinematic equation that acceleration is equal to change in velocity over time, right? Therefore, our force will be equal to mass times acceleration, and that is the second law. So that is our end product there. So was that clear, everyone? So the second law, Newton's second law, is F is equal to ma, right? Or what we're talking about is a proportionality. Something like that. All right. Okay. So the thing is, no. Right. Instead of just writing down F is equal to ma and we just skip the page and move on, right? I just showed you how we got the law itself, right? So this law really speaks to the proportionality of mass and acceleration, right? So it is F is equal to ma. That would be the second law, right? Are there any questions that you would like to ask before we move on to the third law? The third law is really interesting, and we'll have a little some concepts to go through before we move on to the third law. Any
Hold
issues?
on one second.
Oh, hold on.
Alright, can move on now.
All right. I'm not finished with this though, by the way, right? So the units, right? Mass is kilograms, and then acceleration is meters per second squared, right? So this would be the unit, right? But it can also be written as newtons because the unit for force will be newtons, all right? So that's also the unit. All right. So let's move on now, right? Let's cover another concept that we can get from here now, right? Going into impulse that your syllabus states. What is the impulse of a force? What would be that impulse? Remember, I'm going through this with the idea that, this already because I've been late. I didn't have class full time as I should, so probably passed this already. But just recalling that information, what is impulse? What does that speak to? Going once, going twice, going three times. So the impulse of a force, right, is defined as the force, right, that is the force F that is acting on an object for a duration of time t. That is what it is, right? So it is defined as a force acting on an object for a duration of time. So it is a force. Yeah, so that's really what it is, right? It's really a vector quantity as well, right? So impulse is really a vector quantity that has the same direction as the force which causes it, right? So the SI unit for the impulse of a force is really the Newton second, right? So what we're saying is that we have the force, right, for a period of time S, right? S in this case is seconds, specifically stating that because if you say S anywhere, you might say displacement, but in this case, it would be seconds, right? So really and truly, the units now would have been Newton's Newton second, right, or time second. or N times S N S. Alright? That looks like an M actually. So let me just fix that before anybody gets confused there. Alright? So that's what's happening there. So that's the impulse of a force, right? From the impulse of a force, we can get. Alright, so hold on. Before I move on, right? I do not think that you guys did impulse momentum theorem. You guys never did impulse momentum theorem. That's not something that you did.
If we did what, sir?
The impulse momentum theorem.
Oh, no.
Alright. So no. Alright, so we're looking at that. The impulse momentum theorem is literally this. It's this. It's literally that. Alright. But so technically you've done it, but like we never really like specified or picked it out like that. Alright, so looking at that, right? So the impulse of a force, right? So it really looks at the follow through. So if we're going to be exerting some force on, let's say, a box, right? The impulse speaks to how much time we push that, or well, how much time we've spent pushing that box, right? So let's say that we have a box here. We're pushing it at 5 newtons, right? We're looking at how long did we exert that force on that box, right? So the force acting on the object over a period of time, right? So we pushed or we exerted a force of 5 newtons on this box, right? For, let's say, 5 seconds, right? So we're looking at something like that. So just how long, right, or how much time, right, did we spend exerting, right, that force on the box, right, times the force that we exerted on the box, right? So it should be really, really simple, right? Shouldn't be much, all right? So coming from F is equal to ma, we can actually restate Newton's second law, right? So going back into Newton's second law, now I don't know if I'm moving slowly. Can you guys just let me know if I'm moving slowly or you want me to speed up? Because I'm trying to cover all the bases. So F is equal to ma. No need to speed up? Alright. So F is equal to ma. So we're working on this, right? So F is equal to ma. So what can we understand from this? The new statement would have been no. We're talking about the acceleration of an object A, because A is acceleration. The acceleration of an object A, right, is directly proportional to the net force acting on it. We just put acting on it here. And yes, I'll just convert this to a PDF and send it, right? So it's directly proportional to the net force acting on it, right? So we have that as the first part of the statement, right? But this is also inversely proportional to the mass, right? So let me just turn that into a comma. Proportional to the object's mass or to its mass. Or nah, let me rephrase that. Alright, but this should be something that we've seen in some capacity more or less before. Hopefully we have. Alright, So what are we seeing here? We're seeing that the acceleration is directly proportional to the force on an object, right? But the acceleration is actually inversely proportional to the mass. That's what we're saying. That's Newton's second law restated. Alright? Everybody's fine with this. So the first statement that we had up here about proportionality of momentum, right, is the initial statement, right, that we use to get F is equal to ma, right, which is the law, right, and then now the last statement that I have down here is describing F is equal to ma. Force is equal to mass times acceleration. All right. The last concept that I want to look at under the second law of motion would be weight. Can somebody tell me what is the weight of an object? No need to be shy, just unmute and let me know what is the weight of an object.
Mass times gravity.
Mass times gravity, lovely. Right, so looking at it, right? So weight is really defined as the effect. Let me just fix this. Am I recovering from like some type of like neurodegenerative disease? Because like why is my hand? Alright. So it's really the effect of a gravitational field on mass. Field on some mass. Alright? So really and truly, right, we're looking at the acceleration due to gravity, right? We can make the assumption that F is equal to ma, right? And that a would be the acceleration due to gravity when we change it to weight, right? Right? G on Earth would be what? What is the value of little g? Not big G. Big G is different. Are you guys typing in the chat? I need to look in the chat. No, I don't see anything. 9.81. What? 9.81. 9.81 what? Bananas? Like, what is it? What's the unit? Meters per second squared. Because it's an acceleration, right? So it's going to be meters per second squared. Lovely. So that's the concept of weight. Alright, so that's really it, right? So you guys look, I'm not sure if you guys look at the vector nature, right, of the law of motion, or this law of motion, right? So I don't think I'll go into the vector nature completely, right? But what we're saying is that F is equal to ma, right? You guys understand vectors, yes? Completely, you understand vectors and vector components and stuff like that, the x direction and the y direction. You guys understand that, right? Yes. All right. So let me just drop this here. The vector nature of the second law, right? We know that we have different directions, right? We have a y-axis and we have an x-axis, right? If we have a vector of, let's say, 5 newtons in this direction, right? We know that we have an x component here, and we know that we have a y component here. The x component would be the vector, right, which would be like the magnitude of the vector. Right, let's call this vector vector A. Vector A here, it would be A is equal to what? A cos, well, AX, right, would be equal to A cos theta. And then here would be AY would be equal to A sine theta, right? We have all sorts of stuff, right? So what's happening here? When you get the magnitude of the forces, right, and stuff like that, what we can use is Newton's second law to get the force in a specific direction, right? What I'm saying about this is that we can have something like this. The sum of forces in the x direction is equal to the mass of the object times its acceleration in the x direction. And we can also state that the sum of forces in the y direction is equal to the mass of the object times the acceleration in the y direction. Does this make sense? No, it doesn't.
Go over, repeat.
Alright, so let me change this to, let's say, 5 meters per second. Alright, let's say acceleration, right? So what I'm saying is, right, okay, so let's have a look at something interesting, right? Let's look at a scenario, right? So let's say let me see if I can find a scenario. Hold on, let me open this textbook. So it should be on page 94 actually. Alright, so let's look at this scenario, right? So let's say object, right, is on a raft, right? The mass of this object, right, would have been, let's say, the object and the raft really would be 1,300 kilograms, right? That is the mass of the box or the object and the raft that it's on, right? So we're looking at that. All right. The object, right? It's well the hold on. Let me not use an object because I'm not gonna talk about drag and those type of things. Let me change it. Let's say that a man, yes, right. Hold on. That man is extremely embarrassing. All right. Let's say that a man is stranded on a raft, right? This is the raft and that is the man. The combined masses is same, right? So we have that there, right? The man starts paddling or starts moving the raft, right? And he causes an average force, right? P of 17 newtons to be applied to due east of the raft, right? So what we're looking at here, let me move this up here. So the mass of the entire system is, all right, so you have a vector moving in this direction, 17 newtons, right, due east. All right, so it's trying to move in that direction. Okay, the wind exerts a force, right? So the wind is blowing, right, a force A, right, on the raft with a magnitude of 15 newtons that points 67 degrees north of east, right? So what we're saying is that there is another force. Let me just move this over here. All right. So let's name this force, this vector P right here, and let's get another vector, right? And let's say this vector is, well, it's actually 15 newtons, and this is vector A, right? All at an angle of 67 degrees, right? So we've mapped this entire system, right? Ignoring the resistance, right? So air resistance and resistance from water and all these different types of stuff. right? We need to find the x and y components of the raft's acceleration, right? Or of the acceleration generally, right? And then find the forces that are acting in the x direction, the sum of forces acting in the x direction, and the forces acting in the y direction, right? So just looking at something like that, are we able to do a question like this? Are you able to find the components of this of the acceleration here? All right, so we're able to do that, right? So remember from the tables that I've been using, right? We're using the vector, the x component, and we're using the y component, right? If we're looking at this entirely, hold on, let me just set this person to the chat, right? If we're looking at this system up here, right? We have a vector p, right? So let's work with the vector p first, right? In the x direction, what would be the magnitude of its x component? What would be the magnitude of its x component, guys, of vector p in this scenario? Component of x. Okay, so let me just do this. This is the x direction, this is the y direction. Okay, so is that a little bit better for you guys to see? What would be the x component of this of the vector p? The magnitude. Guys. Okay, so I'm seeing you said 17 plus. No man, there's no plus involved there. Cos of 67, right? Well, you have 50. Something wrong. Something is wrong. All right. So let's look at this, right?
Sir, that's a 7 1
Oh, that's for
beside
what?
the 6.
Oh, it's a 7. My apologies. It's a 7. Yeah. Well, I'm going to post the page when I'm done, and then I'm gonna try to get the recordings up. I need to discuss it with you guys after about that. All right. But let's continue here. Alright, so we have the x component here. Since the entirety of vector p is running along the x-axis, can we see that the entirety of vector p is running along the x-axis? It's at no angle to any other axis. It just runs along the x-axis, right? We can say that the magnitude of vector p is fully 17 newtons. You guys can get that? You guys can appreciate that? It's not at an angle to anything. So we don't need to cos or sine anything. We don't need to use an equation. It's fully along the x-axis. Lovely. And then for the y component now of vector p, as we said, vector p is only in x, so it is 0 in y. Right? And then we have another force, a, right? The x component of a, right? So let me get a different color here, and let's derive these x components, right? For a here, we have, let's say, down here, let me just use the green. This would be the x component, and then this would be the y component, right? Hopefully we're seeing that x component and y component, right? The x here would be what side of the triangle? We're looking at the purple vector, 15n. We're looking at A, right? What side of the triangle is the x component of A? Is it the hypotenuse, the adjacent, or the opposite? The adjacent, lovely, right? And then we know that is a cos function that we need to use, right? So remember, cos is equal to what? Cos theta rather is equal to what? Adjacent over what? The hypotenuse, right? And we're trying to find the adjacent. Therefore, the adjacent is equal to the hypotenuse times cos theta. So from that, we get 7. Well, we get 15, right? Cos 67, right? And the y component would be the same thing, but sine, right? So we end up with 15 sine 67. The total now, right? We're looking at the total vector, right? Within the x direction. We're looking at this now, the resultant now. Are we understanding this though? Is this fine?
Can you re-explain it, please? Because I'm getting lost.
Okay, hold on. Give me a second. Alright. So explain the whole thing with cos. Right? It's trigonometry. Right? So what we're saying here, right? Hold on. I really want to complete the angular momentum and stuff like that, but let's do this, right? We have a vector of 15 newtons, right? And it's traveling at an angle above the x-axis, right? So y-axis, x-axis, right? We're trying to find the x component, right? And we're trying to find the y component. We can break the vectors down into components. How much of this 15 newton vector is in the x direction? How much of this 15 newton vector is in the y direction? Do you understand that part? Breaking it down into components. Do you understand that part? Yes, no, maybe, kind of. I need a response.
Yes,
Okay.
sir. Yes,
All
sir.
right. So understand that, right? We can also view this as a triangle. If we were to label the sides, this would be the hypotenuse, right? This would be the angle here is 67, right? So where the angle sits, right? This would be the adjacent, and then this would be the opposite. All right, lovely, right? So from, I'm not sure how far I should go with this, but from SOHCAHTOA, right? We're trying to find the adjacent, right? We do not have the opposite, right? So we don't know the opposite, so we can't really, right, get the adjacent. We're looking for the x component of this 15 newton vector, right? The best thing to use would be our cos, right? Cos theta is equal to the adjacent over the hypotenuse. And in order to find the adjacent, we must transpose to now get the adjacent is equal to the hypotenuse cos theta, right? Because we times by the hypotenuse, and we times by the hypotenuse, right? And what do we get? These cancel, leaving this. That's what we have there. The value of the hypotenuse here is 15 because the vector is 15. Then we cos, and what is the angle? 67. That makes sense, no? Let me erase this line. But yeah, does that make sense now? Was it Shanique who was asking? So that is how, okay, so that is how we get the x component. The y component will be the same thing, but we use sine. Therefore, the cos will just change to sine, right? If you use this method with the table and everything, you literally cannot get a vectors question wrong, right? I think it's virtually impossible. I've been using this method from my lecturer in university, and as of this moment, I've never gotten a vectors question wrong ever. No matter how it gets complex, because you just use a table, make sure that you have the values neatly, use trigonometry to find the components, and you're good. All right. What we're looking at now We're looking at the vectors completely in the x direction, the vectors completely in the y direction, right? That's what we're looking at, right? So we're dealing with forces. Remember, this is gonna be newtons, right? So this is 0 newtons over here. The sum of the forces in the x direction, and we have the sum of the forces in the y direction. The sum of forces in the x direction, 17. Right, the answer here, 15 cos 67 is what? 15 cos 67 is going to be roughly 6 newtons, right? It's actually 5.86, right? But roughly 6 newtons, just for convenience here. And then 15 sine, right, 67 would be roughly 14 newtons, right? We add 17 and 6 is 23, right? 14 and naught is 14 newtons, right? So we have that. What we're trying to look for is the acceleration in the x direction, the acceleration in the y direction, right? We know that the sum of forces from this Newton's second law, right? We're using Newton's second law. The sum of forces in the x direction is equal to the mass of the object times the acceleration in the x direction. And the sum of forces in the y direction is equal to the mass of the object times the acceleration in the y direction. Therefore, acceleration in the x direction is going to be equal to the sum of forces in the x direction. Alright, so let's just do that real quick. Hopefully I'm not going too quickly over the mass. Same thing here. Acceleration in the y is going to be the sum of forces in the y direction over the mass, right? And this is going to be equal to 23 newtons over the 1300 that we stated previously. And then over here it would be 14. That I said 14 and I wrote 15. Alright? But it would be 14 divided by that. The answer here, this would be 0.018 Newton, well, meters per second actually, because this is going to be acceleration. And over here, that should be 0.011 meters per second. Alright? Squared, per second squared, my bad. Alright, and that is how we get the accelerations. So following Newton's second law, so I gave you a scenario where we have vectors acting in two different directions. We find the components. F is equal to ma for the x direction, F is equal to ma for the y direction, and we were able to transpose to find the accelerations. Alright, so that is the question. Let me bubble it. Well, not bubble it, let me just put it in a square. I can't bubble on this platform. But let's see. Alright. So is everything fine thus far? Hopefully everything is fine thus far. That is it for Newton's second law. Newton's third law is what we're going into now. So Newton's third law is really simple, and then we enter
Yes, sir.
into. Alright, lovely. So Newton's third law is really simple, and then we enter into the conservation of momentum. Then we talk about collisions, then into angular momentum, angular velocity, etc. The third law, right? What is Newton's third law? In words, that is. I mean, it's usually just worded. What is Newton's third law? We do the first law, which is the law of inertia. The second law, which is the proportionality, right, of acceleration, mass, and force. And now we're doing the third law. What's the third law? Go ahead. Or is that something in the chat? Go ahead.
For for every reaction, it have an opposite equal reaction or something
Right.
like that.
So we're looking at action and reaction are equal and opposite. Bam. Alright? Action and reaction are equal and opposite. So forces involving direct contact between objects, right, occurs in pairs. So what we're saying here now, if we have a box in contact with a table, right? This is a very ugly free body diagram. Give me a second, let me fix up the free body diagram. Alright? But let's say that we have this box, alright, and we have it on this table here. It's a little bit neater. Alright? So what forces do we have acting on this box? It's not in motion, by the way. It's stationary, it's at rest. What are the forces that we have acting on this box right here? We have the weight of the object, right? And it is going which way? Downwards, leftwards, whatwards? X direction, Y direction. Alright? So it's acting downwards, so acting directly downwards, right? We have the weight of the box, W, right? Let me fix this. Hold on. Why is this not being erased? Get away. Alright. We have the weight of the box, which is equal to what? What is weight equal to? The mass of the box times the acceleration due to gravity acting on the box, right? There's all y no x, lovely, right? Lovely. We have something called a resultant force, don't we? Don't we have a resultant force? So we have the weight of the box pressing into the table, right? And then we're gonna have an
Yes.
opposite. Lovely. And then we're gonna have an opposite force acting out. This is called the normal. The normal force, which is equal and opposite to the weight of the box. Every action has an equal and opposite reaction, right? So we have that there. Gravity is acting down, it's accelerating down, so it's negative 9.81, right? Generally in a system, I would say that it's acting downwards if we're looking at directional, right? But the acceleration towards the center of the Earth would be 9.81 meters per second squared, right? And then we have the normal force, which will just be opposite to interact or to, well, an opposite interaction with that force, okay? So it's fine. Note, if the object is not on another object, like the box is not on the table, then it will not have a normal force. The object has to be touching something to have an equal and opposite reaction like that. If it is falling, there will be free fall, right, occurring, right? There will be a maximum velocity, right? If it's attached to a string, there would be tension, right? If it's swinging, there would be torque and angular momentum and stuff like that acting on the box. But if the box is not actively touching something, right, then we won't have this type of interaction. But there will always be some equal and opposite forces acting on the box, right? It's just focusing on that. So that's what the Newton's third law speaks about, and I spoke to you guys about the fact that it's really, really small. So we're going to head into the conservation of momentum, right, or the law of conservation of momentum. Would we like to take a break before we continue, or we're just moving into the law of conservation of momentum?
Short break would be nice.
A break would be nice. Alright, so we can take like a 5 minute break or something like that. And then we'll return to love conservation momentum. Alright. So let's take this break